Okay, so a continuous random variable is similar to a discrete random variable, but the values of the variable are in fact part of intervals, continuous intervals, rather than taking discrete values. For example, here in this example, we are asked to state whether each of the following represent a discrete or a continuous. The word continuous is missing here. Okay, or a continuous random variable. For example, if we look at the first one, the height of a student in an IB school. Now, the height of a student cannot really take discrete values. Now, the height of students follow a continuous random variable. So over here, this variable is in fact continuous, C for continuous. While the grade of a student in a Math HL course, we know that courses, IB courses, are marked out of 7 and do take discrete values from 0 to 7, 0, 1, 2, 3, all the way to 7. So this variable is discrete. The time spent by an IB student preparing for an exam. Now, the time, we know that a time is a continuous variable. It falls in intervals. It cannot really be having discrete values. So the time spent is in fact continuous. Now, the number of exercises solved by an IB student. Now, the number of exercises, we can either solve no exercises, that's for 0, 1 exercise, 2 exercise, etc. So the number of exercises is discrete. Now, however, the age of students, now the age could be seen as both discrete and continuous, depending on the context of the problem. Now, if we were to be rounding our age every single time you're asked for it, now the variable in that case is seen as discrete. While it could also be considered as continuous because, for example, if somebody says they're 24, they're not really exactly 24, that's a rounded value. So it could be 24 in 6 months or 24 in 5 months and 10 days and 3 seconds, for example. So depending on the context of the problem, the age of people could be either taken as discrete or continuous. So we're going to note this as discrete or continuous depending on the context. Now, similarly to discrete random variables, a random variable that is continuous is also defined by a probability density function. However, the probability density function of a continuous random variable is in fact a function. It's a function that has these two characteristics. It's a function that has to be positive for all x and r, and the integral from negative infinity to positive infinity of f of x is equal to 1. Now, if we were to look at it this way by defining the probability of events using continuous random variables. Now, the probability density function, now it's in fact a function that is defined over r, that is always positive, it's always above the x-axis. Now, if we were to consider this for x equal to a and this for x equal to b, now the area under the curve between a and b is in fact the probability of x being between a and b. Now, for a continuous random variable, the interval around a and b does not really have to be closed or opened. Now, whether it's smaller than b or smaller or equal to b, whenever we're dealing with continuous random variables, it's exactly the same thing. It doesn't really make a difference, unlike discrete random variables. So in fact, what we're seeing here as the integral of f of x from negative infinity to positive infinity is the sum of all probabilities. So this is why that sum is equal to 1. Okay, so if we go through this example here, we consider the function defined by f of x 3x squared for x between 0 and 1, and 0 elsewhere. So show that f is a well-defined probability density function. Now we've just seen that for a function to be a probability density function, it has to satisfy these two conditions. F has to be positive for all x and r, positive, of course, positive or 0, and the integral from negative infinity to positive infinity of f(x) has to be 1. So over here, if we were to check for the first condition, which f of x being greater or equals to 0. Now, over here, if we look at it, we have between 0 and 1, f of x is 3x squared, which is greater or equals to 0. And elsewhere, it is 0. So there are no values of x for which f of x is negative. So the first condition is satisfied. F of x is greater or equals to 0 for all x in R. Now, as for the second condition, the integral from negative infinity to positive infinity of f of x dx has to be equals to 1. Now, f of x is 0 before x equals to 0 and after x equals to 1. Therefore, the integral of f of x over that interval is 0. So we can just drop it. So that would be equal to the integral between 0 and 1 of f of x, because outside this interval, I repeat that f of x is 0, so its integral is 0, so we can just drop it. So between 0 and 1, so I integrate 3x squared between 0 and 1, which is x cubed. An antiderivative of 3x squared is x cubed between 0 and 1, which is 1 minus 0, which is 1. Therefore, these two conditions being verified means that f is a well-defined probability density function. Now, regarding the parameters of a continuous random variable, for the mean, which we know as the expectation, it is the integral between a and b. A and b is the interval over which the probability density function is defined. So, similarly to discrete random variables, to find the expectation, we used to multiply the value of the variable, which we denoted as x, times the probability. So over here, the probability is being defined as integrals. So the expectation would be the integral between a and b from a to b of x, f of x. While the median, we know that the median is the value of x located at the center of the distribution. When it comes to random variables, the median is the value of the random variable that gives a probability equals to half. So this is why now over here, if we're starting the interval between a and b, then the lower bound has to be a. So the value of the median, m, is the value for which the integral from a to m of f of x is equals to half. So it's the interval, it's the upper bound of the interval over which we have a probability equals to half. As the mode of the distribution, the mode of the random variable would in fact be similarly to discrete random variables, where we used to define the mode as the value of the variable with the maximum probability. It's the value that is most likely to occur. So over here, the probability density function being a function over a continuous interval, then the mode is the value of x for which the function, or probability density function, is maximum. And the variance is the integral from a to b of f of x times x minus the mean squared. And of course, the standard deviation is square root of the variance. Now, if we were to look at this example, we have a continuous random variable with a probability density function as follows: 3 over 4x into 2 minus x between 0 and 2, and 0 elsewhere. So we need to first start by finding the expectation. So for part A, we know that the expectation is the integral between 0 and 2. We only consider the interval 0, 2 because elsewhere f of x is 0, so its integral is 0. So we can just drop it. So f of x dx. So f of x over 0, 2, we just multiply it by x to become 3 over 4 x squared into 2 minus x dx. Of course, over here, if you're dealing with a paper where your GDC is allowed, you can immediately evaluate this integral using your GDC. So over here, if we were to use the GDC, the expectation is 1. Okay, now we know that the integral of f of x between 0 and 2 is 1. Well, this is a coincidence here. The expectation is not always necessarily 1. Okay, so that's using your GDC. In part B, we're asked to determine the variance. So over here in part B, we need to find v of x, which is defined as the integral between 0 and 2 of x minus the expectation, which we had it equal to 1, times f of x dx. Again, you replace f of x and you can evaluate your integral using your GDC. So it's 3 over 4x into 2 minus x, that's f of x, times x minus 1 all squared. So using your GDC, the variance turns out to be 1 over 5. So that's using the GDC. Now in part C, we need to find the median. So regarding the median is the value of m for which the integral between 0 and m of f of x dx equals to half. So over here, we cannot evaluate this integral using your GDC because we have an unknown bound, which we need to solve for. So 3 over 4 is a constant. We can just take it out of the integral. So, and we can just expand the x into 2 minus x to be able to integrate easily. Equals to half. So 3 over 4, 2x has an antiderivative of x squared, and x squared has an antiderivative of negative 1 over 3x cubed. So that's between 0 and m equals to half. So replacing upper bound minus lower bound. Now the lower bound is 0. So the antiderivative is 0 for x equals to 0. So that only leaves us with the upper bound. So it's m squared minus 1 over 3 m cubed equals to half. Now expanding and simplifying that expression, we end up with this cubic equation, m cubed minus 3m squared plus 2 equals to 0. Now, using your GDC, polynomial solver, we end up with 3 roots, m equals to 2.732, or m equals to 1, or m equals to negative 0.732. Now, these are rejected because they're outside the interval we're working in. Remember, we're working between 0 and 2 here. Otherwise, the probability density function is 0. So, in fact, the median is 1. So, the median is equals to 1. And finally, in part D, we need to find the mode of this probability density function. So we know that the mode occurs where the probability density function is maximum. So we have f of x to be equals to 3 over 4 x into 2 minus x, which is f of x equals to 3 over 2 by expanding x minus 3 over 4 x squared. And of course, this is for x in 0, 2. Okay, so the maximum, now f is a quadratic function, so the maximum is at its vertex. So f is a parabola, the graph of f is a parabola, so the maximum is at the vertex of the parabola. And we know that the vertex can be calculated by considering negative b over 2a, or if it's another type of function, you can just simply graph the function in your GDC and evaluate the maximum on the GDC. So it's negative 3 over 2 times negative 3 over 4. So the abscissa of the vertex is 1. So the mode is the abscissa. So this is what we're interested in. So f is maximum at x equals to 1, then the mode of the distribution is 1. Okay, so in this example, we have a continuous random variable with a probability density function given by half sine x, where x is between 0 and pi. Of course, when they say between 0 and pi, it means that outside this interval, f of x is 0. Okay, so without using your GDC, sketch the graph of f and hence write down the values of the median, the mean, and the mode. Now, we know that f of x has, or sine x is 0 at x equals to 0. So half sine 0 is also 0. Now for x equals to pi over 2, sine of pi over 2 is 1. So half of sine of pi over 2 is half. That's a half here. Okay, and sine of pi is 0, so half sine pi is also 0. So we have a maximum here. Okay, this is the best I could do here on my touch screen. Okay, so this is sine x between 0 and pi, and we know that at pi over 2 we have a maximum, and we can in fact notice that x equals to pi over 2 is an axis of symmetry of f of x between 0 and pi. So being an axis of symmetry, the function over that interval being symmetrical with respect to one value of x, in that case, the median, the mean, and the mode are all equal to the value of x at the axis of symmetry. So over here, we're going to say that x equals to pi over 2 is an axis of symmetry of f for x between, of course, because if you change the interval, the axis of symmetry could change, or we could lose the symmetry in that case. So then, in this case, we have the median equals to the expectation equals to the mode equals to pi over 2. Now, similarly to discrete random variables, the same way we have a probability distribution defined, the probability distribution function, we can also have a cumulative distribution function, which is the sum of all probabilities from the starting value of x up to the point specified. For example here, capital F of x is the probability of capital X, the random variable, being smaller or equal to x, which in the case of a continuous random variable, it's equals to the integral from 0 to x, because the cumulative distribution function is a function of x, therefore the upper bound is x, it's in terms of x. So it's the integral from a to x, a being the lower bound of the interval, so up to x of f of t dt. Of course, here we cannot use an x as the variable of the integral, of the differential of the integral, because we're already using x at the bound. Okay, so of course where x is between a and b. Now, the integral from a to b of f of t dt is 1. of course, because this consists of the sum of all probabilities over the interval. Now, the probability of the random variable being equals to one value, so the probability of capital X equals to X, is 0 for all X in the interval. Now, over here, it's because this variable consists of continuous intervals, of continuous values. This is not, in fact, a variable that takes discrete values. For example, 0, 1, 2, 3, and in order to say what's the probability of X equals to 2. Over here, this variable is in fact continuous. So what we're saying here is that X is inside a continuous interval. So the probability of obtaining X equal to a specific value is almost impossible. Now let me give you an example in order to help you understand this property better. Now, if we're speaking of, or if we're studying the height of students in a class, and I come up and say, what's the probability that one of you have a height equals to 172.3? Now, that value for height is very specific. And it's more likely that none of the students in the class have a height equal to 172.3 centimeters. I could have someone with a height of 172.35 or 0.2. So, but having 172.3 exactly as a height is more likely to be impossible. So this is why whenever we're finding probabilities using continuous random variables, you'd notice that the events are always intervals, capital X, between two values, smaller than a value or greater than a value, because the probability of the random variable equal to one specific value in a continuous interval is more likely to be impossible. Okay, and now for the third property, this is what we've been using already. The probability of X being between R and S is the integral from R to S of f of t dt. And this is what I've already mentioned in the first part of this video, is that whenever you're dealing with continuous random variables, whether you put that or equal or you don't, is practically the same thing whenever X is a continuous random variable, unlike discrete random variables. Now, if we were to work on this example, we have a continuous random variable X that has a probability density function given by f of X equals to k over x squared plus x for X between 1 and 2. We need to use our GDC to determine the value of k correct to, I mean here 3 significant figures. Okay, so we know, first of all, to find k, we know that the integral between 1 and 2 of f of x dx is equals to 1 because it's a probability density function and we're only working over 1 and 2. Elsewhere, f of x is 0, so we can drop them. Okay, so over here, k being a constant, we can just take it outside of the integral. Now, over here, they specifically asked you to find the value of k using your GDC. So what you need to use your GDC for is to evaluate this integral. Now, over here, using your GDC, by evaluating your integral using your GDC, you'd end up with 0.288 to 3 significant figures times k equals to 1. So this value is found using your GDC. So we divide 1 by 0.288 and we obtain k equal to 3.476. So f of x is 3.476 divided by x squared plus x. Now in part B, hence we need to find the probability of x being between 1 and 1.75. So if you had a new page, a blank page here. So in part B, we need to find the probability that x is between 1 and 1.75. So this is the integral from 1 to 1.75 of 3 of fx, of course, 3.476, that's the value of k, divided by x squared plus x dx. Now, of course, over here you can evaluate this integral using your GDC again, so that's 0.838. That's using your GDC. Okay. Now, in this last example, we have data collected over a period of time suggests that the time t that vehicles have to wait until they can enter the main road of Straight City has a probability distribution function as defined for t between 0 and 2 minutes. We need to find an expression of the cumulative distribution function. Now, the cumulative distribution function is in fact defined as f of t, which is the probability that capital T, or variable, is smaller or equal to small t, which in fact that's the integral from 0 to t. Now over here I chose the upper bound to be t because here we're given the probability density function as a function of t. Consequently, the cumulative density function is also a function of t. So for the function inside the integral and the differential, I choose another variable, which could be x. Okay, so over here, we replace f of x. So 5/6 is a constant. We can take it out between 0 and t of 1 minus 2/5x dx. So integrating, that's 5/6. Integral of 1 with respect to x is x, and integral of x with respect to x is half x squared, which leaves me with 1/5x squared between 0 and t. So over here, simplifying this, upper bound minus lower bound, and multiplying by 5/6, we obtain 5/6 is, for the upper bound t, we have t minus 1/5 t squared. The lower bound is 0, so the antiderivative is 0 at 0. So, which leaves me with the cumulative distribution function to be 5/6t minus 1/6 t squared. Expanding the 5/6, that's the final simplified answer. Now in part B, we're asked to determine the probability of t being between 0.5 and 1.5. So the probability of having t between 0.5 and 1.5, sorry, that's a capital T, that's our variable, is the integral between 0.5 from 0.5 to 1.5 of f of t dt. So over here, that's the integral from 0.5 to 1.5 of 5/6 into 1 minus 2/5t dt. Again, this could be evaluated using your GDC, and your GDC gives you back a value of half for this integral.